Hello, everyone. Good morning, good afternoon. Be welcome to today's webinar, PID tuning for dynamic process even with imperfect data. I'm Vera from Control Station. I work in the marketing department, and I will be hosting this webinar with Damien Moreau from Control Station and Damon Spall from Rotico. And just before we start, feel free to input your questions and comments anytime you want here in the control panel on the GoToWebinar. There is a tab named questions, and you just can type the questions. And after at the end of this webinar, Damien will be answering those questions. And thank you for you all joining us today. So presenting our hosts, Damon Moreau is a Vice President of Partner Development at Control Stations and a recognized expert in process control diagnostics and optimization. With a rich background spanning automation engineering roles in major process manufacturers environment, Damon has a deep track record in driving performance improvements using advanced loop monitoring and PID tuning technologies. And today he will be sharing his expertise in PID tuning for dynamic processes with imperfect data, and an area where his hands-on experience brings key strategies and actionable insights that you can apply right away. And Damon Spall is a group technical director at Rotico and a seasoned expert in industrial automation and control optimization, with extensive experience helping manufacturers improve reliability and performance across complex process environments. Damon brings a practical, real-world perspective to modern control challenges. And for those who are new to Control Station, we have been driving innovation in process control since the 80s. And today we are proud to support customers all around the world, including many of the leading manufacturers across the process industries. And about Rotico, Rotico is an industrial automation specialist delivering advanced technologies that help manufacturers optimize performance. Rotico supports customers in boosting productivity, accelerate time to market, and achieving operational excellence, all backed by exceptional service and a partnership-first approach.
Thanks, Vera. That was a glowing reference there. Really appreciated those comments. Damien, I'm sure you did too as well. Yeah, indeed. See, we've had the agenda there on the screen there now. Just to give you a heads up of what we're going to talk about. Really, today we're talking about data and the model. You know the complications with it and the way to simplify it. We're going to look at how we understand the process. We understand it by the model, and from that, to understand, are we getting, the right information, good data to make good decisions, and how to recognize bad model and bad data. That data collection has gotten easier over the years, but there's still issues with it, and to decipher whether it's a data problem or a process problem is going to be key to that kind of path. Tools for doing it, whether they be software or just your own recipe, your own design of experiment, your own approach to it, is going to be key to that. And we're going to give you a few tips and tricks on that as we go. Obviously we have tools, and we'll briefly talk about those. Finally, we're going to go to like looking at the problems, looking at the things that can cause it, and there's a case study at the end with lots of time for question and answers. As I said, and apologies, as Vera said, get your questions in. If you're coming in with a question, get it into the chat now, and we'll follow up. Won't stop the webinar for them at the moment, but we will certainly circle back to them at the end of the session. First step we're going to go to is a survey. So Vera, can you start up that survey there? And you'll see a blue screen there. How often do you model and tune PID controllers? So, you know, is it select all that apply? I suppose daily is daily, frequently is perhaps weekly, occasionally is monthly, and infrequently is a couple of times a year if you want to use those. So pick one that's appropriate to you, I suppose, and we'll see how the voting goes. We'll give it a few minutes there. Damien, data and how, you know, how often do you approach things? They're always something that you're going to have issues with, I suppose, or how often do you do it? I know, you know, even with all the time that I've been involved with data and analytics, you always have to go, how do I do this again? You know, is the thing when you're approaching a question. But
Yeah,
we'll see how this
absolutely.
goes.
Really interested to see the results of the poll.
Yeah,
Yeah,
absolutely.
I'm going to share the results now.
Okay, so interesting that the strength is occasionally. So that's, you know, once every month, maybe twice a month, I suppose. You know, that's not unusual. So it's long enough to forget how you did it the last time, or at least forget the details of it. You know, daily is low. You know, that, let's be honest here, PIDs are one of the hardest working systems in the industry. You know, yes, we're biased, of course we are, but you know, they continue to work. You know, Damien, what do you think of those? There's a few nice numbers there, I suppose.
Yeah, interesting to see the results come through there, and I think, you know, obviously stand out there for occasionally. So, yeah, very interesting, and obviously not too many there that don't apply. So, a great relevant audience on the call today. Yeah,
yeah, absolutely. You're all interested in the topic. Next slide there.
So before, yeah, good opportunity to share one of my favourite quotes before we jump in, and you know, particularly in relevance to why we use model behaviour. But in the words of George Box, all models are wrong, but some are useful. So yeah, hopefully you'll also find this webinar of use today. But very interesting as we think about models.
Yes, indeed. George is one of those pioneers in statistics. He's worth a look up to anybody on the call. You know, he's got some funny comments and approaches. He actually has a very famous book on statistics called Statistics for Experimenters, and it really does apply to PID control. And whether we like it or not, there's a degree of experimentation with process control, and it's aligning our ideas with our understanding with the data. He was a forerunner of the whole philosophy of DOE, design of experiments. So he really was an innovator from that point of view, and set that term. And really, that's what's so important with this. Your design of experiments, when you come to do tuning, you need a recipe, you need a consistency to the approach. So it's something that really feeds into this. So Vera, can you go to next slide, please? So let's have a look at this one and talk about the model here, I suppose. Anytime you're looking at the data, you're think about the last trend you looked at. If you align your process variable in the upper chart and the output in the lower chart, we're looking for that relationship between these. This is what's called the process model. You see the three red arrows there. Look at the right hand side, how far, first of all. The how far relationship is the output change in the lower chart to the PV response in the upper chart. So it's looking at that, how much did the temperature or process variable move when I move my output? And you can get a ratio there. It's called the process gain. The process time constant is that how fast, how quickly does the process move? It's a time period. Notice that arrow was not pointing at the top of the curve. The process time constant is not the overall time of change. It's, you know, statistically 63% of that time. It's somewhere a little over halfway is where it's calculated. I'm not going to get into too much detail, but maybe whet your appetite to go and if you don't know that, to look for further information. The dead time, the how much delay, is the lag in the process. It's the time from when we asked the change to occur till the change actually started occurring. You know, and if you think of your process, it's the time from when you add new heat to the system till we actually see that on the instrument. The heat has to flow through those steam lines. It has to come through the shell and tube heat exchanger, heat the product in the heat exchanger. The product has to pass out of the heat exchanger to the downstream instrument, and then start to register that value. So it's something that you're always going to have this lag in it. That lag, that delay, we have to wait for it. The control system has to wait for that. So really that dead time is key to getting good control, is that the longer that is, the softer your control has to be. The time constant is how quickly. If the process takes 15 minutes to change, you're not going to be able to change that time into 5 minutes. You know, it's something that it's locked into the process. The how far is the deciding on how much valve we need to move to get the amount of change we want is the thing. So those three numbers are key to understanding your process. If you can understand your process, you can control it. Damien, any add to that? It's hopefully it's quite straightforward and clear there.
Yeah, I think you've explained that one very well, Damien. I think it'd be good to take that thought as we move into further into the deck.
Excellent. Okay, next slide there, Vera.
So I think this is a good time actually to reflect on, you know, why good modelling is important, but more importantly, what poor modelling gives us and the challenges that presents really. So of course, you know, things like inaccurate process models, you know, if we don't get the data side correct, lots of wasted time and effort. I mean, as engineers and, you know, people working in critical process plants and engineering facilities, you know, the last thing we want is to be wasting time and effort. We don't want to be misleading our controller tuning. We need to make sure that that's obviously very accurate, and we need to try and increase the variability as well of the data that we're collecting. I think there's also, through poor data, always a threat, you know, to staff and plant safety. I think that's really important to make sure, you know, that we're not causing any particular safety breaches, and then also, you know, any unnecessary wear and tear as well. I think, you know, the assets and the investments that we make into our plants and the instrumentation, you know, is very, you know, very critical that we maximise the longevity of those components, and we don't want to create any unnecessary wear and tear. So yeah, just a good reminder.
Absolutely, yeah.
Some of the issues that we can find if we don't do the modelling correct.
Yeah, very much so. It's something that, yeah, you know, if we make good decisions, we get good results. If we make bad decisions, if we misinterpret the model and we become too aggressive with our control, we'll start oscillation. That's going to give you wear and tear. It's going to give you increased variability, you know, so it's not going to give you good tunings. Why is the tuning not working for this process? Why are we oscillating? All of those things will feed into that, you know, and, you know, we are playing with real world devices here. These are, and sometimes they're only 1-inch valves, or they could be 24-inch valves. So there is going to be a degree of, you know, real world effects to these changes. You know, it's not it's to make good decisions with good data is the thing. If I was thinking, just as you started that slide, about, you know, if we were in person, I'd ask for a show of hands at about how many times have people in this audience sat for hours or days trying to tune a loop, you know, changing the parameters, trying to adjust it to no good effect, because there's just something not right with that process. It's trying to understand that is going to be key to being able to get the control. So Vera, can you just go to next slide? You know, because that's going to be key to, you know, finding out what's wrong, finding out the cause of my problem here. I always kind of use a why are we here? You know, what, more importantly, why? It's not that perhaps deep and meaningful, but it's, why am I standing in front of this process? What's it not doing for me? I don't think I've ever stood in front of a perfect PID and went, oh my God, that's running amazingly. You know, normally you're called because there's a problem. It's not doing what the operations needed to do. There's a degree of a variation in the system, and it's trying to understand what's not right here, what's not in control. You know, is it a data problem? Is it a tuning problem? Is it a mechanical problem? But using that data to make those decisions, to make those long sample times. If you're not collecting data at the correct frequency, it's going to cause you to not get a true picture of it. You're going to sample and you're going to miss some of the color, I suppose, in the information. Incorrect dead time. Dead time is the killer of good control. If you have a wrong or particularly a long dead time, it's not going to be able to, you have to wait for that dead time. Dead time actually has an important ratio to your time constant. If the dead time is large relative to your time constant, you'll get a poor control. But if you're sampling at a time and you're not getting a respectful or a reflective of the dead time, it's going to then be it's not going to show you the true dead time on it. High noise is always problem on signal, on process noise, instrument noise. You have to minimize those to get a good value for your process data. It's going to be key to that, to getting it. You can see the impacts of the sample time, dead time, and noise underneath. Slow and sluggish response is because of the long dead times. Unstable control if you have incorrect values there. And valve destruction, if there's high noise and high variability, you're going to work that valve longer or further or harder. And every vendor is going to give a warranty or a rating on those pieces of equipment. They have 1 million cycles, which is a huge reliability. But if we use the data incorrectly and put in tuning parameters or over aggressively control, it's going to wear out those. It may not happen today or tomorrow, but you're shortening the usable time of that valve, that system, and it's going to increase your maintenance requirements, etc., to do those kind of things. So it's the impacts that we think about post this is what's going to be key. Vera, just next slide, please.
I think, Damien, just before you jump into the next one, I'd say that that really highlights the issues there around problem solving, and I think you absolutely recognise some of the problems that can occur there, and I think any tools that engineers have available to help them with those problem solving techniques is going to be very valuable. So
correct, yeah. I would say, okay, Vera, just move on to the next slide. We put these slides in the middle of it. We're coming up to the end of the year, so just to let you know about the webinars that will be happening next year. We've got some short versions or descriptions on them. You can scan that QR code, which will bring you to our webinar page, or just go to controlstation.com and look for the webinar tab, and you'll see the agenda and a little bit more detail on the different topics. But just mark your calendar, I suppose. They're about once a month, so hopefully a suitable distance and calendar that you can fit some of them in over the year. Thanks, Vera. Just go to next slide. So we've got a survey question again here. So, thinking about your experiences on data collection and tuning, what sort of data issues do you most find on that? And again, if you have more than one, feel free to tick a few boxes here. Gaps in the data, high levels of noise, low sampling rates, data inconsistency, and process upsets. It's a data issue, but again, it's going to show up in your process. So just take a minute there to look at it. Damien, any which one is going to be a key one for you, I suppose?
Well, yeah, it's hard to say. I think certainly high levels of noise is something that I would expect to be an issue for a number of people.
Absolutely. You cannot tune a process inside the noise band that's on the process. There is an expectation out there that you can tune the noise out of a system, you can react, but you never can. It's whatever process noise is on there or signal noise is going to build into that. Another couple of seconds, I suppose. Whenever you're good, you can step on.
I'm going to share the results.
Okay, a real spread there, which is good. Again, suggests that you've it's good that gaps in the data is low, is what I would say, and that I think we have improved a lot in our ability to collect data. Damien, what are your thoughts there?
Yeah, very, very interested to see that, and I think, as I said, not surprised to see high levels of noise coming in at a quite high percent. But yeah, very, very interesting to see the top one there being the process upsets and drifting processes. I think that's very interesting.
Yeah, absolutely. The frequent process upsets and drifting process is another one of those expectations that there's a falseness to about tuning. Can you come and tune this loop to fix my process? Because well, actually, normally what you get is your PID is not working anymore. Can you come and tune it? Because we're not in control anymore. The PID hasn't changed. It's something in the real world, in the process, that's changed. But we go to the next slide and we can look at these kind of real world aspects of it. This here is this two sides of the real world data coin is for what we're looking here. And this missing data and data gaps, as the statistics show, and it's very interesting. We have gotten much better at data quality and data collection. The science behind that is data storage has gotten less expensive, more capable, and we're getting more data into those. Sample times have improved radically. There used to be a rule of a train of thought or a rule of thumb that 1 minute or 30-minute data was high frequency data. That's long since gone. 1 second data for modern process manufacturing is the benchmark now, really. Somewhere between 1 and 5 seconds is acceptable. Anything after that, then it becomes problematic, really. Noise level, again, as instruments have improved, as measurement devices have improved, as cabling has improved, noise levels have come down radically too, but it still exists or can jump back into the process. It's something that we do see showing up in our data. Part of my why am I here question is I always look back on the data that we have and see when did it change. This is something that happened yesterday, over the weekend, a month ago, or has it always been like this? Because it feeds into that design of experiments as to how I want to understand and what's change do I need to make here. Lags in data processing, again, that's back up to missing data and gaps. The redundancy on systems is really good on this side. If we look to the other side of the coin, and very few just step on, can see that there's the process side of the data is operators don't like to touch. If we want to understand our process, we need to step it. To control something, we must understand it. To understand it, we must see the relationship to it. Systems have oscillations, whether they're process or tuning derived. The model has changed. All of these systems can cause complexities to that. So understanding your process is going to be about getting that data right and stuff. Never settling, oscillating loops, they're just always moving around. Your process is very dynamic, is going to build that complexity into it too. So that, and disturbances. It's a mistake to think that you can tune disturbances out of your process through PID. Disturbances will always be there. You can attempt to minimize them, but if we think about the process model and the rate of change of our process versus the rate of change of our disturbance, gives you that I suppose the problem with that. Disturbances that hurt your process are happening faster than your process, so they're not. We have to tune very aggressively to try and respond to the disturbances, which means we have a high degree of oscillation in our process. Next slide there, please, Vera. So Damien, okay. Filtering. So it's something that. Sorry, I stepped across you there. Go ahead.
No problem at all. Sorry, I was going to say excellent summary on the previous slide, but yes, all around. So working with real world data, I think signal filtering obviously really important, but without wanting to state the obvious here, but just to go over some of the key points. I think, filtering involves smoothing a noisy signal through math manipulation. I think that's hopefully most of the people on the call will understand that. Filtered signals lag behind the raw signal, adding dead time, and of course increasing the time constant. And then through smoother, although smoother, the additional dead time decreases controller performance, and that's seen there in the visual. I'm not sure if you want to expand on that, Damien.
Yeah, absolutely, yeah. So let's think back to that gain, time constant, and dead time slide. So if we look at the jagged line there as the clean signal, what has happened, our process gain between the filtering, and it hasn't changed radically. We're still, for a 5% output change, we're getting a 5% PV change, and it's perhaps there's a 5 or less percent of the overall range of change been impacted by the filter. But really, when filtering kicks in is time constant and dead time. If you look at the difference between the raw PV, actually almost where the arrow is pointing at, and a straight line across to where it hits the filtered PV, that's how much time constant we've added to the time. And it's probably in excess of 50%. We have perceived that the process is running much slower than what in reality what it is. If we tune to that filtered value, the system will get away from us. The system will start to respond much more aggressively to our reaction to it. Dead time, if we look at the dead time, remember, is from when the instant the output changed till the PV started moving in the upward direction. Now, there's not a huge difference here, but it's arguable that on the raw signal, we moved in the upward direction much sooner than when the actual filtered line. So we're adding dead time to our perceived model, which is going to then give us, dead time is the killer of good control. So we're lengthening the dead time, we're killing the ability to respond to it. So filtering is something that really needs to be done with caution, so that in reality you all have filters on your system. There's already filters that are into your instrument. There's going to be a filter there to clean that signal. It's sampling over 1 second, and it's passing out already. Your analog input card is going to filter, so that's going to have another filter. So adding more filters to it, I'm not saying it's wrong, but just be very cautious when you do it, I suppose, is what I would say. Next slide, please, Vera. We have tools that support this. What you're looking at there is our modeling with non-steady state. So if you were to try and calculate the gain, time constant and dead time on that from our classic model calculation, it would be somewhat problematic in finding exactly how much output change was there for PV response, etc. So in automatic, you need tools to support that. We have a unique feature with our tool called non-steady state. You can see the red set point. The lower green line is our output, and the upper blue line, the upper green line is our process variable. That blue line is then our process model, our gain, time constant, and dead time. If you move in, or if you've got younger eyes than me, you'll see down the bottom there that there's a gain, time constant, and dead time value there on that, which is that process model that you can define. The minute that the actual, in that example there, interesting, the process time is 0.2 of a minute and the dead time is 0.25 of a minute. That's not regular, but it's not unusual to see dead time and time constants that are very similar. It doesn't mean you can't control, it just means you have to make the decision on how you're going to control. You have to be much more conservative with your approach on it. Next slide there, please, Vera. So you see on this slide, this is our modeling and monitoring software, Plant ESP. It's going to, if you have a system to proactively collect this data, or at least look for these step tests in your historical process data, you can start to make decisions without impacting the process. Again, we had the problem above that operators unwilling to do step tests. There may be a lot of natural step tests in your process that you can capture this data from. In that example there's 50 step tests that have been collected on that particular process. Similar kind of graphic there, red set point, green process variable, yellow output, with that purple line being the process model, and we can see how well it fits to that data. All models are wrong, some are useful. These models are 3.5 out of 4 there on the model fits, you know, so they're pretty strong fits. But again, there's a degree of wrongness with it. The wrongness is where that purple line doesn't match the green PV line, so it's going to give you that. These kind of tools can compile this information into, you know, you see that fit result distribution there at the bottom. You know, it means that there's a consistency to this data. You're starting to see a repeatable process to it. The distributions have quite are collecting in certain zones. There's always going to be outliers that are the ones that are across the curve on the not matching the bell curve, etc. But there's always going to be outliers on that, which is going to be discounted within these kind of tools. And the reminder for you is look for those. The step tests that you do should be where you operate. You want to be able to control the process where you operate, so you do your step test there at those points. Anything, Damien, there you want to add? There's a lot of data on those pages.
Yeah, no, I think there's you know, some really interesting facts that you've shared there, and I think the visual way of looking at those models is very, very interesting and nice and clear for everybody to see. So yeah, excellent, some excellent points there. Hello. Okay, so thinking beyond PID tuning, so of course, you know, what could be causing the root cause of some of the data issues that we experience. So yes, noise, absolutely. I think it came clearly in one of the surveys that we did. Of course, we can do some filtering, but you know, is there opportunities to resolve bad wiring could be causing it, etc. I think understanding what's wrong with the data flow. You know, we're as engineers, we spend lots of time doing troubleshooting and problem solving, and I think getting to the root cause of the problem is very, very important, and making sure that we understand the data and the flows. And then, of course, you know, what's upsetting the process? You know, what is it? Why are they happening? Why do they keep happening? You know, what can we learn from doing more deeper problem solving and understanding some of these root causes? So yeah, very, very important to consider.
Yeah, absolutely. You know, the noise and filtering, regularly get asked the question, well, what kind of filter can I add? Can I add a filter? How do I filter out that data? Looking at what we saw, it's going to color your information. Your filter needs to be very high frequency in reality. It needs to be, you know, your PID is going to scan at a particular frequency. The filters need to be much higher than that, so they're cleaning out the high frequency noisy signals. Is where the only real benefits you get. You want to remove that instrument and electrical noise. Now, if that instrument and electrical noise is caused by bad shielding, bad grounding in your panels, sometimes they're very hard to change and perhaps even hard to find. Good maintenance practices, people not walking on cables, walking on cable trays, you know, damaging the cables. The science of Faraday's cages around every one of those instrument cables is important. Grounded at one end, we had a short there touching the shield at the other end, etc. Normally those problems get found out on day one of commissioning, but they can creep into a process as well through aging, the insulation breaking down on the shield, etc., causing a ground loop to do that. So noise and filtering is something that you will see from time to time. Is it your instrument starting to fail? Is one of the components on the instrument board starting to die and it's causing noise on the system, I suppose? Is that going to be the problem every time? Probably not, very unlikely, but just start from how was this data running last week, last month? When did this change? Oh, it was directly after the shutdown where we had to replace those instruments. Was the shield correctly terminated? You know, did the instrument guy, when he came in, terminated at both ends of the shield rather than only at the panel end, etc., etc., etc. Try and find the root cause of the problem and resolve it there. You know, so what is wrong with your data flow? Again, our statistics are suggesting, and even the surveys we did, that data flow is getting better. We're collecting data better, but you still have to question it. Are we sampling at the right frequency? Are we getting good data out of that? You know, is what's key to it. The next one is, has this problem been here all the time? You know, is the thing is, so very, you can say we are, but you know, what data is, you know, is this an issue that we've had on the system forever, or has it only shown up in the last while? That troubleshooting. Why am I standing here? I was here a week ago and this process was running perfectly when I tuned it or commissioned it, or we had a shutdown and I did some, we did some work on it. What's changed? Or maybe it's 3 months ago. Has the process sped up, slowed down, changed the density of the material? Has something happened to the process data so that we can say nothing has happened to the process, it's something has happened to our data, to our signaling, to our control, etc. So all of those can feed into that. There are many topics there to cover, but as I said, the key ones are: is the data consistent? Has it been doing this for a week, a month, or a year? You know, and understanding when the change occurred and what's the likely to have caused that change. We just have a quick example here of a success story. So Vera, if you want to go to the next slide there, you can see that, you know, this is, we have a food and bev story here. This is a customer that we have across the globe, multiple locations, multiple uses of our software, and so it's had the ability to detect these problems almost when they happen and highlight them so that you can get in quickly and fix them. Just next slide again, Vera. How do you find a problem starting to happen? You know, well, you know, it could have been there for a long time, but if you have some method of reporting, average absolute error increase, oscillation, frequency of oscillation increase, you know, lack of control, something that is showing you how, you know, it can be maybe the first time you hear it is, you know about it is when you get a high level alarm. You know, if you don't have monitoring systems to proactively look after your process from a PID point of view, the first thing you know about, and it's normally the case, it's when you hit that high or high level alarm due to oscillation increasing and forcing the system to go into higher average absolute error, which gets you to your high level values. We have tools with Plant ESP that will monitor that oscillation. If you have data analytic tools, you can do some of this basic stuff. But as I said, oscillation is key to good control. You know, oscillation is going to be that measurement of is the process, has it the ability to maintain control on it. Next slide is, once you know there's an oscillation or there's a high average absolute error, you can then do something about it. You say, well, what's causing the oscillation? What's the problem we have here? You know, and if you look at other metrics, you can see output travel was high. We were moving a lot. Output travel is the amount of movement the valve, the output makes, the valve makes. You know, it's a function or a reflection on oscillation and average absolute error because the process has changed. You know, now understanding why that process has changed, it will then feed into that, focusing you in on the output travel is high because the oscillation has gone high, and it's going to show you that, yeah, actually we added a new product here. We're running a different recipe where we in this case it was they had increased the flow rate through the process, you know, which caused the variation in the model fit, which then we had to do a tuning change to adjust the parameters to suit it. And again, lack of linearity is everywhere in our processes. We try and remove it by linear valves, consistent processes, design of our heat exchangers, so there's a linear response across a full range of heat transfer, but it's not always perfect, and they can build up into lack of linearities that do it. Damien, any thoughts there just on that kind of my process to go through those, that kind of case study?
I think that was excellent summary there, Damien. I think you know, it's interesting to see that one's from the agricultural industry, but I'm sure there's many multiple industrial sectors that have similar challenges, and I believe I've seen a good selection of case studies as well. I think on your control station website, I think I came across some in the food and bev industry and other process sectors. So yeah, some really interesting information there that's very useful.
Indeed, I would ask everybody to look at our success stories. There's one for multiple industry types, and you'll get some useful insight from that as well. We're just winding up there now. We just go to the next slide. Hopefully we've got some questions in here at this stage. We've a little bit more work to do, but just reminding, if you have a question, get it in there. So this is kind of to just to sum up on the data. Damien, you want to just jump in there first?
Yeah, absolutely. So I think, you know, there's some obviously it's been a very good webinar where you've shared some of the excellent information, Damien, there, and got into some detail. I think just summarising that, some of the key takeaways perhaps for the audience. You know, modelling is essential to PID tuning. I think you know, that's something I'd urge everybody to take on board. We all know that imperfect data is everywhere, so understanding you know, the data sources and some of the explanations you gave of, you know, how to do some of that troubleshooting, really important. We know that some problems are process driven. That's something that we mustn't take for granted. And there are tools there that can improve model accuracy, and I think that's you know, you've given some good examples of that. And I think probably the most important one for me, you know, don't forget to address those root causes. You know, that's a really easy to forget, but critical to making good progress. So yeah, some key takeaways there from a very detailed, excellent webinar.
I love short kind of 1 word, 2 words systems. All models are wrong, some are useful. You know, why am I here? You know, what's the problem, and let's understand the problem. We understand the problem by understanding the process model, gain, time constant, and dead time, and do our tunings match that? If they don't, we need to move. Is the data wrong? Do we have a noise problem? Has the process changed? What's moved our process? And they will be key to it. Back to George Box and the design of experiments. Set yourself up with a recipe for walking through that. You know, if you know your data is good quality, if you know your data is high frequency, good sampling rates, you can discount that, and then you move into your process side. You know, if you know your maintenance practices are good, your instruments aren't starting to scale up, your equipment is not starting to wear out, the plant is only 2 years old. That's not to say that systems won't wear out during those times, but it's always possible to do it. You know, to address those root causes, to fix the problems at source, rather than trying to cover them over with a retune or to adjust your process to it. I think we have one more questionnaire coming there, Vera.
Yeah, thank you. Going to launch now. So this is more contact information. If you want to know more about a easy-to-use PID tuning software, plant-wide control loop performance monitoring solution, the calendar for 2026 for process control and PID tuning workshops is something that Control Station do. The schedule of our webinars for next year, and the link to download our free PID tuning guide. So feel free to choose. You can check all if you want, and then we can proceed for the questions.
Just while we're running there, Vera, do you have a question just to get us going, I suppose? Is there anything coming in over?
So I will start with one here. How do we calculate that time for heating, cooling loops where the heater or cooler might be a good distance from the process equipment?
Yeah, so really, it's as I said earlier about the dead time. Dead time is killer of good control, but understand the process by which when our valve changes to we see that in that value. You can the valve opening, heating up of the system is going to be much slower when you're turning on that system for the first time. Dead time's going to get longer. But if you're up and operating, once you make a change to your valve, it's going to then impact the process. Rough rules of thumb is how far away is your instrument downstream in your pipework, and how many meters per second does it take for the liquid in the heat exchanger to get to your instrument. If your instrument is 1 meter down the pipe or 10 meters down the pipe, and your flow rate to that system is 1 meter per second, you're adding 10 times the dead time to that process. So that's going to be kind of a rough rule of thumb. Understanding the physicals of the process. I have a practical background, so I always believe in standing beside the equipment and understanding how big it is, how slow is it going to be to change, how long does it take for that change to be seen, I suppose is all going to be key to that. Vera, so hopefully that answers that question. Have we another one?
Yeah, sure. So we have some here. This is more on comment than a question, but maybe you can comment here. So none of those reasons are present in our loops. Mainly it's delay times, non-linear process, and things like that.
Okay, long dead times are the killer of good control. Now, as I said, the ratio of dead time to time constant is what gets complicated. It's not that you cannot control a system with a long dead time, you just have to be much more slower or conservative. The bigger the dead time, the smaller your integral term is going to be. Well, just so whether it's over or under the line is going to affect that. You need to be more conservative with your integration of that. So if you have long dead time, tuning parameters are going to get small with the integral, giving less and less addition. We have to wait that time to get to make the action on it. How do you fix that then is the question. The only way to fix it is move your instrument, and which is a hard one, is a hard ask to do it, but it sometimes is the only solution. Move the instrument to much closer to your process change. You mentioned non-linearity. The expectation that you can tune non-linearity processes with one set of tuning parameters is flawed. You cannot do it. What I would say is you tune where you operate, and you then plan for those movements away from operations. You operate at 3 different set points. You should tune at the 3 different set points and change your tuning parameters to account for that lack of linearity in the delta T of your heat exchanger. It could be a lack of linearity through the flow range of operation. You adapt your tunings to operate at a certain set of parameters when you're in the low flow rates, and a different set of parameters in the high flow rates. Adaptive gain scheduling is what it's called. Parameter scheduled control is one of the most underused, most effective methods of non-linear control, in that you can but you need to model in those 3 different zones of operation, and then you generate tunings. Then you just scale your tuning parameters based on where your process variable is operating. The one thing is, don't change it on your set points, change it on your PV. So when I'm between 120 and 140, I use these tuning parameters. 140 to 160, use those tuning parameters, and etc. is the thing. Hopefully that, I appreciate the comments, but yeah, and it is one of the biggest challenges within process manufacturing. How are we doing on time? Okay, yeah.
So we have a few more here, so let's see if we have time to answer all, but if we don't, we will contact you by email to answer your questions. So how do we determine the difference between process disturbances and unsuitable PID tuning?
sorry, the last process disturbances and
Unsuitable.
unsuitable tuning. Okay,
Yeah, PID tuning. Yeah.
So I suppose let's think about our process now. Disturbances hit our processes all the time. We only see the disturbances that are changing quicker than we can respond to. If you ever watch a temperature at a set point and the output changes on its own, but the temperature doesn't move anywhere, that's a disturbance that's happening slower than our process time constant. And the process has been able to change to that time. Disturbances happen all the time in processes. It's the ones that happen quicker is where we have the problem. So that's going to be the one that hits our process faster than we can react to it. Now, the other side of that is the disturbance is going to be hurting our process before we react to it, because the PID is only going to work on error. So the PID is only going to start doing something after that disturbance has already hit us. So if the disturbance is the warm slug of water, the low quality steam temperature, whatever that thing is that's hurting our process is already in our process. And then the PID goes, now I have to work and go after that. You will never remove a disturbance from your process through PID tuning. You can minimize them by changing your process model to an aggressive set of tunings that will react as quick as the disturbance. Problem there is, if your disturbance happens every shift change, when the room, well, you can have disturbances for lots of reasons, but if there's something in your process that's causing this disturbance, boiler rotations, chiller rotations. Now, if that disturbance is coming every 24 hours when we do a boiler rotation, you know it's coming. You can feed forward that disturbance into our control system. Disturbance management is a cascade and a feed forward control philosophy. We do training on it. Please look up our practical process control class and we'll show you methods on how to implement those. Disturbances need to be managed through alternate methods of control. If you can measure the disturbance, you can understand it. And if you can understand it, you can control it. You're going to adapt your output to compensate for this extra load or lower load requirement to occur. Hopefully that answers the question there for you. Damien, I appreciate I'm hogging all of these, but I suppose there's some of them are relatively technical.
Yeah, absolutely. No, that's absolutely fine. I think you explained them very clearly.
We still have time. One more maybe, I suppose.
Sure. So there is one here that's more about our software. So can your software solution be installed on a notebook laptop to be used as a portable tool to visit local equipment rooms in small facilities to analyze local historian data and perform analysis?
So so yes and no. So we have two products. The two products you saw the graphics for there. The first one with the oscillating is our tuning software. Yes, that can be plugged into, installed on a laptop. It doesn't require a lot of horsepower, and it gives you the ability to connect directly into the Rockwell PLC or into the DCS network and pull OPC data, so that you can trend directly into the tuning software, generate the model and make tuning decisions from it. It has some statistical analysis, but very basic data. And in reality, you're only looking at a short window of data. If you want to properly analyze processes, you need to look for relationships, you'll need to look for connections between data, and you need to look at a broader time of data. You know, if I said there's a problem on this PID, you're not going to just go and look at the last half hour or hour of data. You won't going to want to look at the last 3 weeks, 3 months of data to understand it properly. So our monitoring tool is a more holistic tool. It should be installed on the network and connected to, as you said, the historian data. So it's going to pull up that historian data at a regular frequency, and it's going to analyze it and then report out when things start happening. Your control system is there to control, but it's not there to monitor performance decay. The only time you know when the performance decay has occurred on a control system is when you hit a high or low level. You need a monitoring tool that's going to look for performance over time and indicate we're starting to drift, systems are scaling up, etc., etc. So the short answer to your question, yes, there are tools to use locally, to plug in locally. Our tuning software will do that for you. If you want a more holistic monitoring, it's more of a tool that needs to be on the network, looking at the historian data, getting that good quality data, and making good decisions from it.
And you did mention, Damien, around some training available to help people to use the tools. And
yeah, absolutely. We have a super practical process control class. You don't need to use our software to get benefit from it. You will see the benefits of it through the training, but we will give you that design of experiments recipe that you will be able to use to make consistent good decisions. If you look at the gain, time, constant, dead time, they're relatively easy to calculate from clean, clear data. Not every process is clean and clear, but you know, there is that ability. We can show you those skills and tools to develop that process. Process optimization is a ongoing system. You can't just do it today and be done with it. It's something that needs to be nurtured and developed within your organizations. We certainly have the tools and the training to support that.
Thank you all, Damien and Damien's Paul, Damien Moreau and Damien's Paul for this amazing
Damien and Damien. Yes.
Damien and Damien for this amazing webinar. Here is our contact information. So our managers from the US, from Canada, from Europe, from Middle East and Africa. So feel free to reach us if you have any doubt, if you want to hear more about our tools. We are here to assist you. And again, here is our webinar series for next year. I hope to see you all next year with us. And thank you very much. I hope you have a lovely week, a nice holidays on December. And thank you for all to come.
And to our US audience, happy Thanksgiving for Thursday.
That's true. Thanks. Happy Thanksgiving.
Thanks for having me, guys.
Okay, thank you. Thanks very much, Damien. It was good. It was a good chat.